Okay, I think what we'll do is we'll start with what the Gibbs implementation might look like for SSVS. So for your last homework set, that's all I'm requiring for that homework set is just the SSVS portion of the problem. There are choices you need to make. And I'm not going to tell you exactly how to do it, but I can tell you what you don't need to do if you ask me the right question. Something like that. It's basically the x's that I give you in that problem. In one of the test sets, the x's are just like those that are coming in the matrix, and probably all you have to do is standardize the data and add an intercept. For the other problems, you need to transform those x's. So think about interaction terms or polynomial terms of those x's. I tend to think this is sometimes the most important stuff. You know, it's just transforming the data and thinking about what works and what was the relationships you're searching for. So you kind of start with an idea, you explore it. If you start to see signature, you probably start exploring that structure a little bit more. So if you added some quadratic terms and you saw that one of the x's was popping up as significant, it's always in the models, you might say, oh, I'm going to add quadratic terms on that and look at interactions on that. So I probably wouldn't do it all at once and think about every polynomial transformation that I can think of and every other transformation that I can think of and encode this huge X matrix and then say, well, I'm going to search over that. And the reason why is your power to detect things is going way down because you're including so many parameters in the model at once. So you're asking a lot. So start simple and expand out. So the data set 2 and data set 3 require transformations. You'll want to check for linear combinations of things. Maybe I put stuff in there and it's X transpose X inverse. You might form it and it's not full rank. And if that happens, it's because there's a linear combination embedded in there. So possibly I made X17 out of X1 and X2. How did I do it? I added X1 and X2 together and recovered X17. I can hide it even more and take linear combinations with arbitrary weights on those things. So, and that'll mess everything up. So if you're going, this just isn't working, it's probably because you haven't ripped out the multi-collinear terms. So which one do you pull out? Doesn't matter. So in a real scientific problem, it might, like in terms of your interpretation of how you want to think about your results. Mathematically, it doesn't matter. This is just a simulation study. How did I generate the x's and the y's? I did them just like the model suggests. So I even generated the x's as normals. So the x's aren't just hand selected. I used some patterns in normals and maybe mixtures of normals or something like that to make some linear combinations. But it's normal stuff. So that's why if you just center scale it, it'll be fine. You won't mess anything up in doing that. So I've made everything very optimistic. But still, when you come to data set 3, it'll probably be like, I can't quite figure out what the model is. There's a bunch of models in here, they all look about the same to me. And you'll report that. So I think that's real life. That's what I try to do. I never try to give somebody, here's the best model. I like to walk in 10 competing models and say, here's what they have in common. So what I'm going to teach you that stuff like stepwise selection doesn't do is stepwise selection can pick its best model and say it's got variables x1, x4, and x17 in there. That's the best model. And then you say, okay, what's your second best model? And they say x2, x3, and x15. No overlap. What? How can this be? So the second best model doesn't contain they don't contain each other in any way. That's if you ended up selecting off of p-values, stepwise selection, and you use p-values as your criterion, that can happen. And why is that? Because of the non-additivity of everything. What is a Bayesian doing? They're putting a posterior measure on it, and if you increase the set, you increase the measure. And so that will imply there's some natural nesting in the models. So x1, x4, and x17 are really good in model 1, then the second best model might contain those or might drop one of those variables, but they're going to be somehow nested in each other. That I think is really important. So fit criterions and posterior probabilities are very different things in that sense. If you don't believe me, there's thousands of papers written exactly on that, and I've written a couple myself. So, you know, beating up on p-values, I've gotten tired of that. So, of course, there's always problems in real data sets. How do you calibrate the alternative hypothesis? I've tried to make that obvious. In this problem, if you standardize your data, you might have an obvious choice for your alternative variance, and it'll work very well. In real problems, it's not like that. How do you even standardize what makes sense? Depending on the nature of the data, how I compare it to itself, the columns of x depends on what those x's are to me. So I don't always just subtract off the mean and divide by the standard error. So it doesn't always make sense to me. Okay, you won't have to think about that for this assignment. I'm going to go through the Gibbs outline real quickly, and then we're going to jump to Markov theory. I'm going to try to tell you what a limiting distribution is. I'm going to try to tell you what a stationary distribution is. I'm going to try to show you that Metropolis Hastings stationary distribution is the posterior target. So I'm going to try to do that relatively quick, so I'm going to have to tell you what the idea of proofs are as we're building everything up. My definitions I'm going to give to you won't be like how they say in a stochastic process class. So positive recurrence, I might say, you're in a state and you can come back in a finite amount of time, and we can make that mathematical rigorous. All states can go from anywhere to anywhere, not just in one step. So that's the positive recurrence criterion, things like that. It means the whole network of states is connected. So if you can go anywhere from anywhere eventually, and you always come back, you'll explore. So those two criterions are required in Metropolis Hastings. I just said them. So we could spend a week on definitions and little problems getting us to identify how these conditions work. We can make lots of homework problems about those. That's what a stochastic process class would do for you. There's also another criterion, aperiodicity, and it means that there's no funny patterns in how you cycle through everything. If it were like deterministic, that I go from any state to any other state and I keep coming back exactly the same path, or there's like a pronounced signature in how you do it, you keep repeating that same signature, that'll mess everything up as well. And so we need to make it so that there's no funny patterns in how you cycle and you're actually doing it randomly. So there's three conditions, they're called the ergodicity conditions. So I just gave you 2 weeks right there. I'm going to start with that in mind and launch from there. Let's go through the Gibbs outline for stochastic search variable selection. The reason I keep saying volatility on that V is there's something called the stochastic volatility model. And so if you study finance, you'll know what it is. So there's a really cool dynamic linear model representation that I'm enamored with. A lot of my friends are enamored with. I still remember those homework problems. I don't do finance, but I still like the model. So that's where my confusion keeps leaking out. Every time I see V, I want to say volatility. Variable selection, that's what we're doing. Let's go to DocCam again. I like this so much. And I think I might stick to this, we'll see. But I wrote it all down for you. So we're going to walk through that. And to keep you guys comfortable, I printed it out for you. So you can have one of these on your way out. And it has both of those things on it. It's exactly the same thing. So let's just look through it. Here's how you might implement the stochastic search volatility modeling. Just keep in mind all it is it's normal hypothesis testing. But we're testing a whole bunch of stuff and we're kind of testing them together and testing them apart and trying to think about what is the Bayes factor for the complete model and not just one variable at a time. When you nest all this in a Gibbs sampler, you end up getting joint inference. So So if we were to just do one sample, one line of the Gibbs sampler and repeat that over and over again and never change the index, we're just doing hypothesis testing that is conditional on whatever else is in the model. When we free everything up and cycle through everything and make decisions, we're making joint decisions and figuring out what the joint model is. So this is Sam's question, where he said, can I come up with a Bayes factor for more complicated hypotheses? This is searching through all of them for you. So that's kind of cool. This is avoiding searching through all 2 to the p models out there. And if p is large, that's huge. And so it's making it so that the amount of time you spend on each model after burn-in is proportional to its probability. So you spend more time computing things concerning models that are relevant. So I like that. That's a Monte Carlo property. Okay, so here's our basic setup. So there's our problem, y's, x's. You'll need to transform all those x's. So what I mean is you might make a column in here where you've got some column. This won't be automatic. You're not going to be using a program to search through all of this. You could. I can conceptualize making one, but you're going to just reformat this X matrix. So you might have terms that look like this. X I2 squared. So you might take all your xi2 columns, so all these things, and square them out. So you make a new column where you do that. Or you might have this thing in xi3 times this one squared. So there's an interaction between a squaring of that variable and something else. So I mean they covary together. And that explains some of the variability in everything. So this is just Stat 101, exploratory analysis. They have you do these things. I think we all enjoyed it. We kind of did an investigation and played around, and maybe they taught you about Box-Cox transformations, and you're trying to optimize something. It's like that. So this is the best fit. I've got my penalty terms. That's all baked into this. It's not meant to be complicated. So I have an original X matrix. I might grab a column of it, square everything else, and put that column into the new X matrix. This is like real life. Somebody gives you, here's the data. If you just start working with the data in the way that they handed it to you, there's only one algorithm in the world that I know that will not suffer horribly if you just use the data in the way they hand it to you. And that's like CART will do that. But all this stuff, you'll mess it all up. So you need to encode all those things and assign a covariate that's attached to it. You need to be really specific in your ordering which columns are represented, and when you're tracking columns that are coming in and out of this matrix, depending on your selection step, you need to track that. I'm not going to tell you how to do it. You have to just think about what your data structure is. I would always compare everything to the original matrix and keep everything formatted so it's like, oh, this covariate means that thing. So at the end of each loop, you track what it means in the original way that you encoded it. You're allowed to be creative. The only thing I didn't do is I didn't make any thing that wasn't polynomial. I didn't invert any of the x's or do anything like that. So the y's are on the original scale. You don't need to transform the y's. I included up to pairwise interactions, a couple, not a lot. So I didn't just riddle it with those. That'll mess you up. And I didn't use anything bigger than cubic polynomials. So there could be a term in there where I've got xi2 plus xi2 cubed. Something like that. So that's, I have the main effect in there. And I also have the other one. And I'd probably encode those as two different columns. So I might have these things in there, and I have the cubic terms. So just because you cubed them and put them in doesn't mean that the uncubed versions aren't there. So again, exploratory stats. If you've ever taken a regression class, that first one you teach, without a lot of theory, that one. Okay. So X is my original matrix. I'm going to call it star up there. That's X, but you've transformed that and played around with it. Don't get crazy first. Run it on maybe just the main effects, and then do some transformations later. So if you just try to do the most complicated stuff, write up your code the first time, see if it works, you're going to be in miserable land. So if you start simpler and then you progress, you'll be okay. Okay. Let me just give you some notation real quick. I'll clarify this in a second. Let X current be the full matrix, the current X at that iteration. So when you start the loop, you have an X in hand. We're going to be modifying that X by either subtracting out columns or adding in columns. On your first step, your first iteration, X current is probably full X. So you could pick random X too, but you might start with it being full. At the next step, you're going to choose a jth column. So when I talk about the jth column, I mean with respect to the original X. So I'm always going to just randomly select a column. If that column isn't included in X current, you're going to include it in. If it is included, you're going to consider removing it. So now you're going to have 2 copies of X that are off by 1 column. So X star, I'm going to say, is X current plus or minus the jth column. Does that make sense? Cool. We can format 2 variances and 2 expectations. The formulas are the same as you're familiar with. They're the rich formulas. So if I just used a normal prior on everything and I worked out the variances and the expectations, these are what I would get. So just these, oh, I'm sorry, right here, that's a star. So let me fill that in. It's going to be missing from the notes just because I photocopied it from here, but I can spot an error. Do you mind? So this one is a star. Looks good. And I compute my expectations and my variances. From those, I can compute my Bayes factors. So the way I set it up is so I don't have to keep flipping over that Bayes factor. It's going to work out that I can use the Bayes factor in the same form. So if I'm adding in a column, that might look upside down from that Bayes factor before that I was always explaining it in terms of removing a column. So this will have the effect of always using the exact same Bayes factor if we just reformat X and recycle their names at every step of the loop. Here's the Bayes factor. It's the same as what we wrote down before. The only thing that's a little bit different is that dimensionality thing. So the dim of that thing, I called it the dim of E star. I could have called it the dim of V, but V is P by P, or P plus 1 by P plus 1, or P minus 1 by P minus 1, depending on which direction we went. So that's just going to get that right, and it has the effect of flipping over this Bayes factor, if need be. So I compute that Bayes factor. I'll just show you. Here was our Bayes factor last time. This is what we had on the board before. This was the Bayes factor. And this was always related to removing the variable, and that's why that's P minus 1. I've subtracted out one of the columns effectively. And that's P right there. But if I'm adding a column, then this might be P and that might be P plus 1, or whatever that dimension is. Keep in mind what P was is the original matrix size. And all that's going to be changing is that matrix at every step of the iteration, shrinking and expanding. Shrinking and expanding around the X's that are actually driving the model. So I've just kind of rewritten this a little bit, same exact idea. And now I've got that Bayes factor and I don't have to keep inverting it. If you want to do it where the smaller model is always on top, you might be flipping that thing upside down depending on if you're trying to add that column in. So you can do something like that. The dimensionality of whatever E is, it's the dimensionality of the betas that are in that model. So and E is on that exact same scale. So it could have been dimensionality of the betas that I'm thinking about, something like that, but I just thought dimensionality of E star would work in your code. So, and then I just encode this e to the plus 1/2 term, and I'm just E star squared times the variance inverse. So that was that completion of the square term that we kept coming back to. And we have the corresponding ones in the numerator and the denominator. So the numerator is the one that we're going to. That's either an expanded matrix or a shrunken matrix. And the downstairs one is the one we're comparing it to, what I've called the current. Here's the algorithm. So here's how you might proceed. There's lots of implementations of this. What I'm going to do is I'm going to select J uniformly from 1 to P. P is my original matrix size. So after you've transformed everything and said these are the columns I'm going to explore and see which ones explain why well, that's whatever your P is. So this P is not going to be smaller than the P that I gave you for the problem. And that's going to be true for every data set in there, even test set 1, because you're going to have an intercept. So it's going to probably be 1, whatever the dimension is, plus 1. That'll work for test set 1, just to get you started. We should probably all agree that on the same sort of model. So go compare your model to everybody else. I don't care if you write on the Slack, did everybody get this model? So for test set 1, don't do it for test set 2 and 3. If you do it on test set 3 and everybody comes up with different things and then you guys are freaking out, it will have had the intended result minus the freaking out part. Probably will agree maybe on some of the main effects, but some of the interaction terms would be hard to capture. So if J is not in X current, so I'm adding that J in, just keep in mind if I say J is the third column, I'm talking about J of my original matrix, putting that column in the right place. So I would say this whole exercise is really creating a data structure that adapts this matrix and tracks which column you're adding and subtracting. So a little bit of mental exercise. I like thinking through problems like that. How would I design this code to do that really nicely? You can always work with a copy of X itself and then work with the betas themselves and just turn the betas and turn them into the corresponding zeros. It would be the exact same calculation. But you'd have to still think about how you encode these things. Okay, so if J is not in X current, then X star is X current plus the Jth column from the original thing. So I'm going to be sliding that in. If J is not in X current, then I'm removing the Jth column. So I'm going to just pull that thing out. Hardest part of the problem is just mapping what J means back to the original matrix. Then I'm going to compute a posterior probability. So this is the posterior probability of including or excluding that variable, how much we like it or not, the change that we've made. And we're just taking that Bayes factor that we wrote down up here, inverting it, multiplying by the inverse ratio of null priors. I'd probably take them to be a half-half. You know, at every step of this algorithm, that's the uniform choice. You can change those around if you want. I would say I don't like doing it because I just don't like people freaking out when I do it. But I would say if you wanted to induce a sparser prior on everything, you could say, I think that variables aren't in there. So I'm going to pick, you know, pi naught to be 0.1 and 1 minus pi naught or something like that to be large. So you could do that. I usually think what matters more is the continuous part of the prior. And so I want to talk about it through the alternative variance, but even more than that, the tail behavior of everything. And that was our brief discussion about sometimes you might use Cauchy's. So when I use that to kind of push the variables out. Saying that, if you just needed a quick knob to turn, and you like the dynamics and the asymptotics of what I've taught you already, you could just play around with those things right here and make sparser models. You'd have to kind of know, is the model I'm looking for sparse or dense? And I think scientists and engineers sometimes know this for their problems, but in the context of this, you kind of don't have any rationale for thinking one way or the other. I'll tell you this, they're relatively sparser models. So in a sea of noise. Except for data set 1. That one's a dense model. Or it's relatively sparse, but I didn't give you a lot of key to begin with. So I'd say it's pretty dense in there. So what you're gonna do, generate your index, which variable you're gonna try to include or exclude, compute that probability, and then I just wrote this in real briefly. I'm gonna flip a coin with that probability. If this is a 1, then I'm gonna take x current to be x star. So I'm gonna make the move, change the matrix. Otherwise, x current is already x current. So I don't need to change that here. You'll probably wanna track the frequencies of the models visited in this part of the loop and set up some sort of a tracker in there that, oh, I keep including the gate variable or something like that. So that at the end of the day, when you're exploring how often did I visit that model, you have a quick way of tracking it. And you don't have to look over all these x's that are changing sizes, because somehow you'd have to look through some dictionary anyway to figure out what those columns were, unless you have some really smart way of encoding it all. Does that kind of make sense? So it's just a coin flip at every time. You could implement this different. I could march through all the variables in here. I kind of like just writing it down like this. It's just a randomization step, not a predetermined step. But you could do it both ways. And in expectation, the algorithms run the same. So they'll converge the same in expectation. It'll be a little bit different because changing something will be a little bit different, but it'll only muck around with the burn-in. What else can I tell you about that? So you're going to code this thing up. If you get totally lost on this and it's just not working, you can go find some software that implements this. There's a lot of packages out there that do this, and you can run it on everything. But please also show me that you attempted the problem and that, geez, I don't know what's wrong. So there's a safety net in there.
How does the burn-in behavior of this compare to like a GIF sampler?
It is a GIF sampler.
Right. So
it compares equivalently.
Right.
But all GIF sampler, like, what is it? How does it compare to the GIF sampler that I have you code up for mu and phi?
Yeah, I guess that's what I was asking.
It takes a lot longer to burn in, a lot longer. And it kind of depends on what your starting point is. If you start with, keep in mind, through each iteration here, I can only remove or enter in one column. And so I could probably do things fancier, but maybe I'd be too ambitious in making too big of steps.
And then you'd have to do like a joint phase factor for each step.
That's right.
And
so,
updated.
Yeah, and why would you do that? There's not great reasons over this, but this can take a while to converge. Stochastic volatility, since we brought it up, I remember sitting there going, this will never converge when I coded that. I guess I'll let it run for like 3 more hours. It just was not long enough. And there was a problem with what's called a discounting factor. And so everything was pushed up against a boundary, messing everything up, and it turned out I needed to change that one little thing and discount in a slightly different way, and everything converged in like 6 hours, and I was really impressed. But you don't know in the middle where you're just watching this thing go berserk for a while. And then finally it grabs onto the tail of the distribution, and it says there's a signature, and it starts climbing up it. So it depends on your starting positions. That can be really difficult sometimes. Okay, cool. You guys want some Markov theory? Let's do it. I'm going to explain everything in discrete land, but everything I say transitions to continuous land. So where the states are anywhere in a continuum. It's a little bit easier to write out using matrices and get the idea using matrices. So if you don't like this view of the world, you can think of your continuous space as a discrete thing that's chopped up as infinitely fine as you want, just not infinitely fine. And that is reality. So I think this actually is the right view. Einstein said that the world is a Markov process. We just don't know the states and the probabilities. Question, do you believe it? Einstein said. Does that work? I do not believe it. I just do not believe in concepts like this. He changed his opinion later, and he said, I don't believe God rolls dice. So he was trying to clarify his earlier statement. No, I don't believe this anymore. So he didn't even believe it.
Wasn't he referring to spooky action resistance when he said, I don't believe God was...
I have a book called Ideas and Opinions. He said a lot of things. So lots of quotes. He's a frustrated philosopher. So he doesn't know what to believe about a lot of things. And a lot of scientists get into this trap. But they're doing this to figure out how the whole universe really works.
Why do you not like the Markov theory, just out of curiosity?
I don't think it's Markov.
Is it because you don't...
I think there's interactions between
think the
things.
entire universe can just be represented by some amount of states, even if it's...
Yeah, it's just a probability between transitioning between them. I just don't think it's like that. So why should it be? Just because we wrote that down?
Yeah.
So Stephen Wolfram said it's cellular automaton. Same idea. Make some funny patterns out of it. That doesn't mean because zebras have stripes that look like what you can create out of cellular automata. That's not a convincing enough argument for me. It's just not enough. Saying that, my answer is I don't know how the universe works. So I'm okay with that.
I'm very disappointed.
I'm a bad philosopher. Okay, Markov chain. I think we've all seen it before. Let's just make sure that we understand the representation. So I'm going to think about my Markov chain is matrix X. These have some entries. I'll call them AIJs in here, where what these look like, A11, A12, all the way to A1N. This is going to be AN1, AN. I'll call this M1, M, and N. So just some matrix, some probabilities in here. Aij is the probability of starting in state I and moving to state J. So this is the probability of starting in state 1 and moving to state 2. So there's different states and they represent things. So my current state is Bayesian Statistics professor. So what was the probability that I would be here? Pretty high. So it wasn't 1. So where was I earlier? How did I transition? Those probabilities were pretty determined. What am I going to do later today? I've got like 4 things. Tomorrow's even more questionable. I don't know what I'm going to do, when I'm going to be able to do it. So, but I would like to have some fun since it's my birthday. So I've got like 5 meetings, so I'm going to try to fit in some fun stuff, and there's some probabilities attached to it. So that's what that is right here. I just want to relate an equation to you. This is a common equation that we often see. This looks like this. So this is the probability of whatever, I'll still call it state J, given state I. But it doesn't matter. This is some random variable. This is some random variable. It's just a conditional probability statement times the probability of being in state I. What would you like this to be equal to? So I'm going to sum over all the I states. What would you like that to be equal to? Yeah. Probably the probability of state J. It just feels so natural to us because this is just basic marginalization. What does this actually mean? This is the steady state of being in state I and the steady state of being in state J. Those are those margins. We call them the stationary probabilities. So these are the probabilities that if I sampled with those probabilities, if I actually knew the steady state of being in a particular state after a long run of something, I could sample with those probabilities, feed them through my transition matrix, A, and go to some other state, and it will preserve that steady state. That's what it means to be steady state. It's kind of a physics term, but I think we know what it means. We hear it all the time. So if I sample from the stationary distribution, the steady state, I transition through with those Markov probabilities, I stay in that steady state, stationary distribution. So if I go through the Markov process and I stay back in that same distribution, that's called the stationary distribution, and that's why it means that. If a Markov chain has those three properties that I told you about, you can get around, you can come back without any funny patterns, then this Markov chain will have what's called a limiting distribution as well. We're going to study that as the same, and the limiting distribution is the steady state. That's how we use Metropolis Hastings. So we're iterating through this thing a large number of times, these Markov transitions, and watching it converge to some steady state. So we're actually using the limiting distribution to find the stationary distribution. I'm going to rewrite this using matrix A. So I'm going to call this right here pi, I. This is going to be pi j. So I can format a vector of all of my steady states across all of my states. I can call that vector pi, and I can rewrite this equation. This equation can be rewritten like this. A transpose pi is equal to pi. I transposed everything. Just if you look at the definition of this, where the I comes up and where the J comes up, everything is transposed. So this, transposing that matrix the way we usually write it, is the right way to do it. So remember, the IJ element right here is getting switched around right here. So just be careful about that. So this is A transpose pi is equal to pi. Does this equation look familiar to you? Ever see anything like it? This is just a matrix, special properties. But what is that sort of equation?
Is it like an eigenvalue thing?
It's just like an eigenvalue thing. So if I had a lambda here, then it looks just like an eigenvalue problem. This eigenvalue right here is still there. It's 1. So what it's saying is Markov chains always have an eigenvalue of 1. And that's true. So why is that? It has to do with the sum 1 constraint of the columns of everything. So all of these, because these are probabilities, is I sum through this. This is summing over j conditional on I. It sums to 1. So I should probably write that down. The sum of the probability state j given state I, where I sum over all the j states, that's equal to 1. Turns out how fast you mix through a Markov chain is related to the second eigenvalue problem. You can prove that the eigenvalues are all bounded by 1 in here. And it's that gap between the second eigenvalue and the first eigenvalue, they call it the spectral gap. This is pretty high level stuff. It's how fast you move through the Markov chain. So in an ideal world, if we were implementing Metropolis Hastings algorithms, we would want algorithms with very small spectral gaps. They're fast to converge through everything. That's a lot of theory. That would take a semester at least. You can come up with bounds on it. You can rarely write it down, especially in continuous land. It's not so easy. It's just solving this real easy eigen problem. It's not a simple thing, especially when you don't know the truth, but there is theory that can tell us about bounds in the right direction that makes them useful. Those are called Chernoff bounds. Okay. So that's what a Markov chain is. So we've already defined what the stationary distribution is. So this is the same vector right here. If you want to know what's happening in the burn-in period of Metropolis Hastings, you're not yet in stationarity, and that burn-in period is the mismatch in this equation. That it's not the same pi on every step that you're moving through. When you're feeding everything back in and doing the next iteration, pi hasn't stabilized yet. But once it does, and you're in the stationary distribution, you won't move from it. So you just sit in that distribution, just like we've seen in our examples. Okay, a limiting distribution. Here's a question. How do we find the two-step transition matrix? Let me just be more clear about this. So this is the one-step transition matrix. It tells us how to step. But once I step through once, I get some state. So let's say I started in state I. I'm going to pick some state to go to. Maybe it's this one right here. This is my new state, J. And so maybe I did this. I really just sampling from these probabilities, a multinomial, doing a coin flip and deciding which side I landed on. So which state am I in? Let's say I moved to state J. So let's say J was down here. So then what I'm going to do is I'm going to start at J here for the second step and see where I land on the next iteration. So I move from I to J. Then at the next step, I go from J to somewhere else. Let's say this was K. So this right here, that process would be probability in the first step of how I moved, and then probability in the second step of how I moved. So I have to account for both of those. How do you write down the transition matrix? We could work through all these probabilities and figure it out. It's just conditional probabilities. So, how? So you can almost see it. If you can't, just write these out right here using that definition. Replace all of them, and you'll see something very obvious occurs, that these make sense probabilistically, how you transition through. So this is going to be A2. Really easy to do. I just take A, I square it. And that's the probability of being in the kth step after two transitions. This is an easy one if you understand that. That's that. So the limiting distribution is when I power this up to infinity and see what this all converges to. So let's do that. So here's my Markov chain. I have probability 0.5 of starting in state 1 and winding up in state 1, but I could also move to state 3. I can't move to state 2 there. If I'm in state 2, some probability of staying there or moving to state 1, or some probability of moving to state 3. So, and there's some probability of moving to state 1 or state 2 from state 3, but I can't stay there, so it's forcing me around. So it turns out there's a signature for whether or not a limiting distribution exists. So let me just show it to you. A squared, boom. Got some numbers. Okay, that's very interesting. That's the two-step transition. A3, got some numbers. That's the third step transition. Just repeating that Markov process. We start to see something happening. I'm going to make it 10. And somebody tell me what's happening. Did we skip too many? We need to do 5, 6, 7. Let's go to 11. Let's go to infinity. Yes, that is infinity. 100 in my class. Good enough. What we've noticed is these all converge to the same probabilities right there. So what that means is that there's a limiting, in the limit of all of this, there's a 0.6292 probability of being in state 1 after a long run of everything. Some probability of being in state 2, some probability of being in state 3. So it doesn't hang out in state 2 very often. So that's low probability. I could figure that out a little bit differently. I could try to solve this equation and solve for it. And what you would do is you would say, I'm going to take this thing, see what the stationary distribution is. I'll take A transpose pi minus pi I, so that I can subtract from both sides. This is going to be the 0 vector, however many states I have. So this would be 3-dimensional for my problem. Here, there's only 3 states. But then I need to include this other criterion right here. Sum of the pi i's is equal to 1. So that's easy to do. I can end up pulling that pi out from right here. I can put in a bunch of 1s in here, and I can append 1 over here and multiply this by pi and solve that system. So this is the stationary probability part, and this is the sum 1 constraint. So I multiply pi by all 1s. I'm just adding up all of pi and saying that they're equal to 1. So now I have a linear algebra problem that I can solve. I don't have to do an eigenproblem to solve this. That's really nice. I already know what the eigenvalue is. So that helps us out a lot. And I can write that out like this. Same thing. Those are those numbers. So did the solve. If you do the solve and you don't put in the sum 1 constraint, you're going to get something crazy. And if you try to just normalize it to make it right, you will do something crazy. So you could get negative numbers, all kinds of weird stuff in here. Okay. That's limiting distributions and stationary distributions. What I want to show you next time at the very beginning is that the Metropolis-Hastings algorithm converges to the posterior target, and that is the stationary distribution. Let me show you one more equation. This is what I call the super equation. It has a real name. It's called detailed balance. It is the key to figuring out if your algorithms are correct. I usually include a proof like this or something like that in the context of my algorithm to show everybody this actually is right. I have this probably the #1 question my colleagues will come and ask me about. I came up with a MH algorithm. Reviewer asked me, does it adhere to detailed balance? I don't know how to check. After a while, you get so good, you can just look at their algorithm and go, oh yeah, it does. No, you're good. You want the proof? Now you got it. So you'll get good at recognizing this after a while. But this is the equation. So this is going to be probability. I'm just going to talk about theta as my set of spaces, or my set of states. It can be continuous. So I'm going to now move to a continuous view of the world. So I'm going to say theta is a state in omega, and theta prime is another state. It's going to represent like theta in our posterior distribution, the thing that we're sampling from. So I'm going to write it down like this. So P theta prime given theta times pi theta is equal to P theta given theta prime pi theta prime. This is called detailed balance. It looks like an equation you're already familiar with. Just like this other thing that we were playing around with. It just seemed natural. We just had to interpret what it all meant. So the stationary distribution is like the marginal distribution, but there's this process that you're following that you arrive to it. So this kind of looks and feels the exact same way. These are going to be our Markov transitions. Probabilities. They're not probabilities in continuous land. It's a continuum. There will be probabilities attached to this problem because I do make a discrete decision in the Metropolis Hastings process that I flip a coin with some probability and decide to go or not. So there's a continuous aspect to it and there's a discrete aspect. And instead of going back and forth between the words density or probability, I'm going to just use this word rate. And that's the typical rate that we'll invoke next time, and we'll see it in our proof. So MC transitions, that's the MC transition. We're going to have to encode this with what Metropolis Hastings tells us to do. And this is the stationary probability. So both of those are stationary. And we could map this back to exactly this definition by integrating over both sides, either with respect to theta or theta prime. It will marginalize out one side of it. It'll sum up to 1 on one side, but it doesn't sum up to 1 on the other side. And we'll come back to that equation. Let's pick up with this next time. It's called detailed balance. The only part that's different from things that you know is these are like in order. So in Metropolis Hastings, this might be like the for loop running in advance, forward in time. So I go from iteration I to I plus 1. This is where things get a little different, is this is asking what happens backwards in time, moving backwards. So there's all this lingo on the reversibility of the algorithm and what happens in both directions and proving that it's time reversible, or in which ways is it not time reversible, so on and so forth. And that's a discussion you'll hear from researchers that work in this field. They'll prove maybe it's time reversible, or they say, my algorithm's not time reversible, but I have this other guarantee. So leapfrogging is like that. Anyway, Gibbs isn't absolutely time reversible. So if I update A, B, C in the forward direction, the other direction backwards is updating C, B, A. So it's not strictly time reversible. It's not time reversible in a very trivial sort of sense. It doesn't mess with the convergence of anything. Anyway, I'm going to just leave that out of our discussion and not talk about the directionality of this, and we can just think of them as conditional probabilities. And it doesn't matter if it's forward or backwards. That's the part of it that gets technical. If I can leave that out, I can have a proof in 10 minutes. So there's a whole Markov chain class, minus all the examples and problems. And then we'll jump right into Dirichlet processes. Dirichlet processes I can explain as a Gibbs sampler what people actually do, and I can leave out all the theory on that and tell you that, oh, it's got all these special properties, and if I can prove this is a valid, mixture sampling algorithm and tell you what the measure means. I can write up those papers, or I can just tell you how to do it. So we'll do the engineering 101 version, and then we'll at least know how to do it, and then if we write a paper, we can chat GPT like some technical discussion and insert it in.